Management Engine Deep Dive, Understanding the ME at the OS and hardware level, and it is by Peter Boss. Please welcome him with a great round of applause.
Right, so can everybody hear me? Nice, okay, so welcome. Well, this is me. I'm a student at Leiden University, and I've always been really interested in how stuff works. And when I got a new laptop, I was like, how does this thing really boot? I knew everything from the reset vector onwards, so I wanted to know what happened before it. So first I started looking at the bootguard ACM, and while looking through it, I realized that not everything was as it was supposed to be, and that led to a later part in the boot process being vulnerable, which ended up in me discovering this. And I found out here last year that I wasn't the only one to find it. Drama Hudson also found it, and we reported it together, presented it at Hack in the Box. And then at the same time, I was already also looking at the management engine. Well, there had been a lot of research done on that before. It was mostly, the public info was mostly on the file system and on specific vulnerabilities, which still made it pretty hard to get started on reverse engineering it. So that's why I thought it might be useful for me to present this work here. So it's basically broken up into three parts. The first bit is just a quick introduction into the operating system it runs. So if you want to work on this yourself, you're more easily able to understand what's in your face in your disassembler. And then after that, I'll cover its role in the boot process, and then also how this information can be used to start developing a new firmware for it or do more security research on it. So first of all, what exactly is the management engine? There's been a lot of fuzz about it being a backdoor and everything. Well, in reality, it's if it is or not depends on the software that it runs. It's a processor with its own RAM and its own I/O MMUs and everything sitting inside your south reach. It's not in the CPU; it's in the south reach. So when I say this is going to be about the 6th and 7th generation of Intel chips, I mean mostly motherboards from those generations. If you run a newer CPU on it, it will also work for that. So yeah, bit more detail. CPU it runs is based on the 8486, which is funny. It's quite an old CPU, and it's still being used in almost every computer nowadays. So it has a little bit of its own RAM. It has quite a bit of built-in ROM. It has a hardware accelerated cryptographic unit, and it has fuses, which are write-once memory that's used to store security settings and keys and everything. And then some of the more scary features. It has bus bridges to all of the buses inside the south reach. It connects the RAM on the CPU, and it connects the network, which makes it really quite dangerous if there's a vulnerability or if it runs anything nefarious. And its tasks nowadays include starting the computer, as well as adding management features. This is mostly used on servers where it can serve as a board management controller, do like remote keyboard and video. And it does security, bootguard, which is the signing of a firmware and verification of those signatures. It implements a firmware TPM. And there's also a SDK to use it as a general purpose secure enclave. So on the software side of it, it runs a custom operating system, which parts of which are taken from Linux, the teaching operating system by Andrew Tannenbaum. And so it's a microkernel operating system. runs binaries that are in a completely custom format, and yeah, it's really quite high-level system actually. If you look at it in terms of the operating system it runs, it's mostly like Unix, which makes it kind of familiar, but it also has large custom parts. And yeah, like I said before, in this talk I'm going to be speaking about 6th and 7th generation Intel Core chipsets. So that's Sunrise Point, Lewisburg, which is the server version of this, and also the laptop system on the chips that they're just called Intel Core Low Power. They also include the chipset as a separate die, so it also applies to them. In fact, I've been testing most of the stuff that I'm going to tell you about on the laptop that's sitting right here, which is a Lenovo T460. And the version of the firmware I've been looking at is 11.00.12.05. Right, so I do need to put this up there. I'm not a part of Intel, nor have I signed any contracts to them. I found everything in ways that you could also do. Didn't have any leaked NDA stuff or anything that you couldn't get your hands on. Also, it's a very wide subject area, so there might be some mistakes here and there, but generally it should be right. Right. Well, if you want to get started working on an ME firmware, want to reverse engineer it or modify it in some way, first, well, you got to deal with the image file. You've got your SPI flash. Most of its firmware lives in the same flash chip as your BIOS, so you've got that image. And then how do you get the code out? Well, there's tools for that. It's already been extensively documented by other people. And you can basically just download a tool and run it against it, which makes this really easy. This is also the reason why there hasn't been a lot of research done yet. Before these tools were around, you couldn't get to all of the code. The kernel was compressed using Huffman tables, which were stored in ROM, and you couldn't get to the ROM without getting code execution on the thing. So there was basically no way of getting access to the kernel code, and I think also to the system library. But that's not a problem anymore. You can just download a tool and unpack it. Also, the Intel tool to generate firmware images, which you can find in some open directories on the internet, has Qt resources XML files, which basically have the descriptions for all of the file formats used by these ME versions, including names and comments to go with those structure definitions. So that's really useful. Right, so when you look at one of these images, it has a couple of partitions. Some of them overlap, and some of them are storage for it, and some is code. So there's the main partitions, the FTPR and FTP, which contains the programs it runs. There's MFS, which is the read-write file system it uses for persistent storage. And then there is a log to flash option, the possibility to embed a token that will tell the system to unlock all debug access, which has to be signed by Intel, so it's not really of any use to us. And then there is something interesting, the ROM bypass. Like I said, you can't get access to the ROM without running code on it. And the ROM is mass ROM, so it's internal to the chip. But Intel has to develop new ROM code, and they have to test it without respinning the die every time. So they have the possibility on a unlocked pre-production chipset to completely bypass the internal ROM and load even the early boot code from the flash chip. Some of these images have leaked, and you can use them to get a look at the ROM code even without being able to dump it. It's going to be really useful later on. So then you've got these code partitions, and they contain a whole lot of files. So there's the binaries themselves, which don't have any extension, and there's the metadata files. So the binary format they use has no headers, nothing included, and all of that data is in the metadata file. And when you use the anonymizing tool, you can actually, it'll convert those to text files for you, so you can just get started without really understanding how they work. Yeah, so the metadata It's tag length value structure, which contains a whole lot of information the operating system needs. It has the info on the module, whether it's data, code, where it should be loaded, what the privileges of the process should be, a checksum for validating it, and also some higher level stuff such as device file definitions if it's a device driver or any other kind of server. I've actually written some code that uses this. It's on GitHub, so if you want a closer look at it, some of the slides have a link to GitHub file in there, which contains the full definitions. Right, so all of the code on the ME is signed and verified by Intel. So you can't just go and put in a new binary and say, hey, let's run this. The way they do this is in Intel's manufactured time fuses, they have the hash of the public key that they use to sign it, and then on each flash partition there's a manifest which is signed by that key, and it contains the SHA hashes for all the metadata files, which then contain a SHA hash for the code files. There doesn't seem to be any major problems in verifying this, so it's useful to know, but you're not really going to use this. And then the modules themselves, as I've said, they're flat binaries mostly, and the metadata contains all the info the kernel uses to reconstruct the actual program image in memory. And a curious thing here is that the actual base address for all the modules, for all the programs, is the same across an image. So if you have a different version, it's going to be different. But if you have two programs from the same firmware, they're going to be loaded at the same virtual address. Right, so when you want to look at it, you're going to load it in some disassembler, like for example IDA, and you'll see this. It disassembles fine, but it's going to reference all kinds of memory that you don't have access to. So usually you think maybe I've loaded out the wrong address, or am I missing some library? Well, here you've loaded it correctly if you use the address from the metadata file, but you are in fact missing a lot of memory segments. And let's just take a look at each of these. It's calling it, so it should be code. And it's pushing a pointer there, which is data. And what's that? So it has shared libraries, even though it's flat binaries. It actually does use shared libraries because you only have 1.5 megabyte of RAM. You don't want to link your C library into everything and waste what little memory you have. So there's the main system library, which is like libc on a Linux system. It's in a flash partition, so you can actually just load it and take a look at it easily. And it starts out with a jump table, so there's no symbols in the metadata file or anything. It doesn't do dynamic linking. It loads the pages for the shared library at a fixed address, which is also in the shared library's metadata, and then it's just there in the process memory, and it's going to jump there if it needs a function. And the functions themselves are just using the normal System 5 x86 calling convention, so it's pretty easy to look at that using your normal tools. There's no weird register argument passing going on here. So right, those shared libraries, there's two of them, and this is where it gets annoying. The system library, you've got access to that, so you can just take your time and go through it and try to figure out, hey, is this open or is this read, or what's this function doing? But then there's also another, second really large library, which is in ROM. They have all the C library functions and some of their custom helper routines that don't interact with the kernel directly. Such as the strings functions, they live in ROM. So when you've got your code, and this is basically where I was at when I was here last year, you're looking through it and you're seeing calls to a function you don't have the code for all over the place, and you have to figure out by its signature what is it doing. And that works for some of the functions. It's really difficult for other ones, so that really had me stuck for a while. Then I I managed to find one of these ROM bypass images, and I had the code for a very early development build of the ROM. This is where I got lucky. So the actual entry point addresses are fixed across a entire chipset family. So if you have an image for the server version of like the 100 series chipset, or for a client version, or for a desktop or laptop version, it's all going to be the same ROM address point. The ROM addresses. So even though the code might be different, you have the jump table, which means the addresses can stay fixed. So this only needs to be done once, and in fact, when I upload my slides later, there is a slide in there at the end that has the addresses for the most used functions. So you're not going to have to repeat that work, at least not for this chipset. So if you want to look at a simple module, you've loaded it. Now you've applied the things I just said, and you still don't have the data sections. In fact, I don't know what that function there is doing, but it's not very important. It actually returns a value, I think, that's not used anywhere, but it must have a purpose because it's there. Right. So then you look at the entry point, and this is a lot of stuff. And the main thing that matters here is on the right half of the screen there is a listing from a Minix repository. And on the left half there is a disassembly from an ME module. So it's mostly the same. There's one key difference though. The ME module actually has a little bit of code that runs before this C library startup function. And that function actually does all the ME specific initialization. There's a lot of stuff related to how C library data is kept, because there's also no data segments for the C library being allocated by the kernel. So each process actually reserves a part of its own memory and tells the C library like any global variables you can store in there. But when you look at that function, one of the most important things that it calls is this function. And it's very simple. It just copies a bunch of RAM. So they don't have support for initialized data sections. It's a flat binary. What they do is they actually use the BSS segment, so the zeroed segment at the end of the address space, and copy over a bunch of data in the program. The program itself is not aware of this. It's really in the initialization code and in the linker script. This is also something that's very important, because you're going to need to also at that address in the data section, you're going to need to load the last bit of the binary. Otherwise, you're missing constants, or at least initialization values. Right. Then there's the full memory map. To the processes themselves, it's a flat 32-bit address space. It's got everything you expect in there. It's got the stack and the heap and everything. There's a little bit of heap allocated right on initialization. This is basically how you derive the address space layout from the metadata. Especially like the data segment and the stack itself is like the location varies a lot because of the number of threads that are in use, or the size of data sections. And also those stack guards, they're not really stack guards. There's also metadata for each thread in there. But that's nothing that's relevant to the process itself, only to the kernel. And well, if you then skip forward a bit and you've done all this, and you look at your simple driver, like this is taken from a driver used to talk to the CPU. Okay, so when I say CPU or host, by the way, I mean the CPU, like your big Skylake or KB Lake or Coffee Lake, whatever, your big CPU that runs your own operating system. Right, so this is used to send messages there, but if you look at what's going on here, okay, I think I have a problem with the animation here. It sets up some stuff and then it calls a library function that's in the main syslib library, which actually has the main loop for the program. That's because Intel was smart and they added a nice framework for device driver implementing programs, because it's a microkernel, so device drivers are just userland programs calling specific APIs. Then there's normal POSIX file I/O, no standard I/O, but has all the normal open and read and IO, CTL, and everything functions. And then there's more initialization for the server library. And this is basically what all the simple drivers look like in it. And then there's this. Because it's so low on memory, they don't actually use standard IO or even printf itself to do most of the debugging. It uses a thing that's called Sven. I'll touch on that later. So there's the familiar APIs that I talked about. It even has POSIX threads, or at least a subset of it. And there is all the functions that you'd expect to find on some generic Unix machine. So that shouldn't be too much of a problem to deal with. But then there's also their own tracing solution, Sven. That's what Intel calls it. That name is in all the development tools that you can download from their site. And basically, they don't include format strings for a lot of the stuff. They just have a 32-bit identifier that is sent over the debug port, and it refers to a format string in a dictionary that you don't have. Whereas one of the dictionaries for a server chipset floating around the internet, but even that is incomplete. And the normal non-NDA version of the Intel developer tools has some 50 format strings for really common status messages it might output. But yeah, like if you see these functions, just realize it's doing some debug print there. It might be dumping some state or just telling it it's going to do something else. It's no important logic actually happens in here. Right, so then for device files, they're actually defined in the manifest. When the kernel loads a program and that program wants to expose some kind of interface to other programs, its manifest will contain, or its metadata file will contain a special file producer entry, and that says, you have these device files with a name and an access mode and a user and group ID and everything, and the minor numbers. And the kernel sends this to the, or not the kernel, the program loader sends this to the virtual file system server, and it automatically gets a device file pointing to the right major and minor number. And then there's also a library, as I said, to provide a framework for a driver. And that looks like this. It's really easy to use if you were a ME developer. You just write some callbacks for open and close and everything, and it automatically calls them for you when a message comes in telling you that that happened. Which also makes it really easy to reverse engineer, because if you look at a driver, it just loads some callbacks, and you can know by their offset in the structure what actual call they're implementing. Right, so then there is one of the more weird things that's going on here, how the actual userland programs get access to memory map registers. There's a lot of this going on. Calls to a couple of functions that have some magic arguments. The second one you can easily tell is the offset, because it increases in very nice power of 2 steps. So it's probably the register offset, and then what comes after it looks like a value, and then the first bit seems to be a magic number. Well, it's not. There's also an extension in the metadata saying these are the memory mapped IO ranges, and those ranges they each list the physical base address and a size and the permissions for them. Then the index in that list does not directly correspond to the magic value. The magic value, actually, you need to do a little computation on that, and then you can access it through those functions. The computation itself might be familiar. Yeah, so these are the functions. And the value is a segment selector. So they use actually don't use paging for inter-process isolation. They use segments, like x86 particular mode segments. And for each memory mapped IO range, there's a separate segment, and you manually specify that. Which is just weird to me. Like, why would you use x86 segmenting on a modern system? Minix does it, but yeah, to then extend that even to this. Luckily, normal address space is flat, like to the process, not to the kernel. Right, so now we can access memory mapped IO. That's all the like the really high level stuff. So what's going on under there? It's got all the basic microkernel stuff, so message passing, and then some optimizations to actually make it perform well on a really slow CPU. The basics are you can send a message, you can receive a message, and you can send and receive a message where you basically say send a message, wait till a response comes in, and then continue, which is used to wrap function calls. This is mostly the same as in Minix. There's some subtle changes which I'll get to later. And then memory grants are something that only appeared in Minix really recently. It's a way for a process to basically create a new name for a piece of memory it has and give a different process access to it just by sharing the number. These are referred to by the process ID and the number of that range. So the process IDs are actually local per process. So to uniquely identify one, you need to say process ID plus that number. And they're only granted to a single process. So when a process creates one of these, it can't even access it itself unless it creates a grant for itself, which it's not really that useful usually. And these grants are used to prevent having to copy over all the data inside the IPC message used to implement a system call. Yeah, these are the basic operations on it. You can create one, you can copy it to and from it. So you can't actually map it. A process that receives one of these has to say to the kernel using a system call, please write this data into that area of memory that belongs to a different process. And then there's also indirect grants, because in Minix, they do have this, but also only recently, and usually if you have a microkernel system, you would have to copy your buffer for a read call first to the file system server and then back to either the hard disk driver or the device driver that's implementing a device file. So the ME actually allows you to create a grant pointing to a grant that was given to you by someone else, and then that grant will inherit the privileges of the process that creates it, combined with those that it assigns to it. So if the process has a read-write grant, it can create a read-only or a write-only grant, but it cannot. If it only has a read grant, it cannot add write rights to it for a different process, obviously. So then there's also some big differences from Minix. In Minix, you address a process by its process ID or thread ID with a generation number attached to it. In the ME, you can actually address IPC to a file descriptor. Kernel doesn't actually know a lot about file descriptors. It just implements the basic thing where you have a list of files, and then each process has a list of file descriptors assigning integer numbers to those files to refer to them by. And this is used so you can, as a process, you can actually directly talk to a device driver without knowing what its process ID is. So you don't send it to the file system server, you send it to the file descriptor, and the kernel just magically corrects it for you. And they moved select into the kernel. So you can tell the kernel, hey, I want to wait till the file system server tells me that it has data available, or till a message comes in. This is one of the most complicated system calls the ME offers that's used in a normal program. You can mostly ignore it and just look like, hey, those arguments are the file descriptor sets as a bit field, and then there's the message that might have been received. And there's DMA locks, because you don't just want to write to registers, you actually might want to do the direct memory access from hardware. So you can actually tell the kernel to lock one of these memory grants in RAM for you. It won't be swapped out anymore, and yeah, it will even tell you the physical address, so you can just load that into a register, and it's not really that complicated. It's just lock it, get a physical access, write it into a register, and continue. Well, that's the most important stuff about the operating system. The hardware itself is a lot more complicated, because the operating system, once you have the code, you can just reverse engineer it and get to know it. The hardware, well, let's just say it's a real pain to have to reverse engineer a piece of hardware together with its driver. Like if you've got the driver code, but you don't know what the registers do, so you don't know what a lot of the logic does, and you're trying to both figure out what the logic is and what the actual registers do. Right, so first you want to know which physical address goes where. And it's the metadata, the listings I showed you actually had names in there. Those are not in the metadata files themselves. I annotated those. So you just see the physical address and size, but there's the one module, the bus driver module. And the bus driver, it is a normal user process, but it implements stuff like PCI, configuration space accesses, and those things. And it has a nice table in it with names for devices. So if you just run strings on it, you'll see these things. And yeah, when I saw this, I was pretty glad, because at least I could make sense what device was being talked to in a certain program. So the bus driver, it does all these things. It manages power gating to devices. It manages configuration space access. It manages the different kinds of buses and IOMMUs that are on the system. And it makes sure that the normal driver never has to know any of these details. It just asks it for a device by a number assigned to it at build time. And then the bus driver says, okay, here's a range of physical address space that you can now write to. So that's a really nice abstraction. And it also gives us a lot of information, because the really old builds for Sunrise Point actually have a hell of a lot of debug strings in there as printf format strings, not as Sven catalog IDs. It's one of the only pieces of code for EME that does this, so that already tells you a lot. And then there's also the table that it just talks about that has the actual info on the devices and names. So I generated some DocuWiki content from this that I used myself, and this is what's in the table, part of it. So it tells you what address the PCI configuration space lives at. It tells you the bus device function for it through that. It tells you on what chipset SKUs they are present using a bit field, and it tells you their names. In different fields, it also contains the values that are used to write the base address registers for PCI, so also their normal memory ranges. And there's even more devices. So the ME has access to a lot of stuff. A lot of it is private to it. A lot of it is components that also exist in the rest of the computer. And there's not a lot of information on a lot of this. These are basically all the things that are out there, together with the conference slides published by other people who have done research on the ME. I did not have time to add links to those, but they're easy to find on Google. I'll get later to this, but I actually wrote a emulator for the ME, a partial emulator, to be able to run ME code and analyze it, which obviously needs to know a bit about the hardware, so you can look at that. There is some files in Intel's debugger package that in specific versions of that have really detailed info on some of the devices, also not all of it. And I wrote some tool to parse some of the files. It's really rough code. I published it because people wanted to see what I was doing. It doesn't work out of the box. And there's a nice talk on this by Mark Ermolov and Maxime Goriachi. I don't know if I'm pronouncing that correctly, but they've done a lot of work on the ME, and this particular talk by them is really useful. And then there's also something else. There's a second ME in server chipsets, the innovation engine. It's basically they copy-pasted the ME to provide a ME that the vendor can write code for. Don't think it's used a lot. I've only been able to find HP software that actually targets it. And that has some more debug strings, but also not a lot. It mostly has a table containing register names, but they're really abbreviated. And for a really small subset of the devices, there is documentation out there in a Pentium NNJ series datasheet. It seems like they compiled their LaTeX code or whatever with the wrong defines, because it doesn't actually fit into to the manual that well. It's just a section that has like some 20 tables that shouldn't be in there. Right, so this is from that talk I just referenced, and it's an overview of the innovation engine and the bus bridges and everything in there. This isn't like very precise. So based on some of those files from System Studio, I tried to get a better understanding of this, which is this. This is the entire chipset. The little DMI block in the top left corner is what connects to your CPU. And all of the big blocks with a lot of ports are bus bridges or switches for PCI Express like Fabric. Yeah, so there's a lot going on. The highlighted area is the management engine memory space, and the rest of it is like the global chipset. Well, the things I've highlighted in green here are on the primary PCI bus. So there's this weird thing going on where there seems to be two PCI hierarchies, like at least logically. So in reality, it's not even PCI, but on Intel systems, there's a lot of stuff that behaves as if it is PCI. So it has like bus device function numbers, PCI configuration space registers. And they have two different routes for the configuration space. So even though the configuration space address includes a bus number, they have two completely different things with each of which has its own bus 0. So that's weird also because they don't make sense when you look at how the hardware is laid out. So this is stuff that's on the primary PCI configuration space that's directly accessed by the North bridge on the ME CPU. So that's the minute IA system agent. System agent is what Intel calls a North bridge nowadays. Now that's not a separate chip anymore, and it's basically just the North bridge and the crypto unit that's on there, and the stuff that's directly attached to the North bridge being the ROM and the RAM. So the processor itself is, as I said, derived from a 486, but it does actually have some more modern features. It does CPU ID, at least on my systems. Some other researchers said theirs didn't. It's basically the core that's in the Quark MCU, which is really great because it's one of the only cores made by Intel that has public documentation on how to do ROM control, so breakpoints and accessing registers and everything over JTAG. Intel doesn't publish this stuff except for the Quark MCUs because they were targeted at makers. But they reused that in here, which is really useful. It even has an official port to the OpenOCD debugger, which I have not gotten to test because I don't have a JTAG probe, which is compatible with Intel voltage levels and supported by OpenOCD. And it also has, like I said, CPU ID and MSRs. It has some really fancy features like branch tracing and some more strict paging permission enforcement stuff. And they don't use the interrupt pins on this. So it's an IP block, but if there's some files out there, that's where this screenshot is from, that actually are used by a built-in logic analyzer Intel has on the chipset, and you can select different signals on the chip to watch. Which is a really great source of information on how the IP blocks are laid out and what signals are in there, because you basically get a tree view of the IP blocks on the chip and some of their signals. They don't use the legacy interrupt system. They only use like message-based interrupts where the device writes a value into a register on the interrupt controller instead of asserting a pin. And then there's the North bridge. The North bridge is it's partially documented in that datasheet I mentioned, and it does support x86 I/O address space, but it's never used. Everything in the ME is a memory space or exposed as memory space through bridges. The North bridge implements access to the ROM, RAM. It has a I/O MMU, which is only used for transactions coming from the rest of the system. And it's always initialized to, like you said, at least in the firmware I looked at, it's always initialized to the inverse of the page table. So linear addresses can be used for memory mapped, for DMA. It also does PCI configuration space access to the primary PCI bus, and it has a firewall that actually allows the operating system to deny any IP blocking the chipset from sending a completion on a bus request. So it can actually say, hey, I want to read some register, and only these devices are allowed to send me a value for it. So they've actually thought about security here, which is great. Then there's one of the most important blocks in the ME, which is the crypto engine, and it does some of the more well-known crypto algorithms, AES, SHA hashes, RSA, and it has a secure key store, which I'm not gonna told a lot about it in their ME talk at Black Hat. And a lot of these things have DMA engines, which all seem to be the same. And there is no other DMA engines in the ME, so this is also used for memory-to-memory copy or DMA into other devices. Yeah, so that's used in a lot of things. This is actually a diagram which I don't have the vector for anymore, so that's why the LibreOffice background is in there. I'm sorry. So this is basically what that crypto engine looks like when you look at that signal tree that I was talking about earlier. The DMA engines are both able to do memory-to-memory copies and to directly target the crypto unit they're part of. Basically, when you, I don't know about the control bits that go with this, but when you set the target address to 0 and the right control bits, it will copy into the buffer that's used for the encryption. So that is how it accelerates memory access for crypto. And these are the actual register offsets. They're the same for all of the DMA engines in there, relative to the base address of the subunit they're in. And then there's the second PCI bus, or bus hierarchy, which is like in some places called the PCI fixed bus. I'm actually not entirely sure whether this is actually implemented as a PCI bus as I've drawn it here, but this is what it behaves like. So it has all the ME private stuff that's not a part of the normal chipset. So it has timers for the ME, it has the implementation of the secure enclave stuff, the firmware TPM registers, and it has the gen device, which I've mostly ignored because it's only used at boot time. It's only used by the actual boot ROM for the ME mostly. It is what the ME uses to get the fuses Intel burns. So that's the Intel public key, and whether it's a production or a pre-production part. But it's pretty much a black box. It's not used that much, fortunately. There's the IPC block, which allows the ME to talk to the sensor hub, which is a different CPU in the chipset. It allows it to talk to the power management controller and all kinds of other embedded CPUs. So it's interprocessor communication, not interprocess. Confused me for a bit. And there's the host embedded controller interface, which is how the ME talks to the rest of the computer when it wants the computer to know that it's talking. So it can directly access a lot of stuff, but when it wants to send a message to the EFI or to Windows or Linux, it'll use this. And it also has status registers, which are really simple things where the ME writes in a value, and even if the ME crashes, the host can still read the value, which is actually how you can see whether the ME is running, whether it's disabled, whether it fully booted, or whether it crashed halfway through, but at a point where it could still get the rest of the computer running. And there is some core boot code to read it, and I've also implemented some decoding for it on the emulator, because it's useful to see what those values mean. Right. So then there's something really interesting, the primary address translation table, which is the bus bridge that allows the ME to actually access the PCI Express fabric of the computer. For a lot of the, what I in this table call ME peripherals that are actually outside the ME domain in the chipset, it uses this to access it. It also uses it to access the UMA, which is an area of host RAM that's used as a swap device for the ME, and a trace hub, which is a debug port. But it also has a couple of windows which allow the ME to access any random area of host host RAM, which is the most scary bit, because UMA is specified by host, but the host DRAM area is, well, you can just point it anywhere, and you can read or write any value that that Windows or Linux or whatever you're running has sitting there. So that's scary to me. Right. So, and then there's the rest of it in the rest of the devices which are behind the primary ATT, and that's a lot of stuff. That's debug. That's also all the normal peripherals that your PC has, but it's also includes things like the power management controller, which actually turns on and off all the different parts of your computer. It controls clocks and resets, and so this is really important. And there's a concept that you'll come across when you're reading Intel manuals or ME-related stuff. That's root spaces. Besides your normal addressing information for a PCI device, it also has a root space number, which is basically how you have a single PCI device exposing two completely different address spaces. And it's 0 for the host, it's 1 for the ME. Some devices expose the same information on there, other ones behave completely different. But yeah, that's something you don't usually see. And then there's the sideband fabric. So besides all of the stuff that I just covered, which is PCI-like, at least, there's also something completely different, sideband fabric, which is a completely packet switch network where you don't use any memory mapping by default. You just have a 1-byte address for a device and some other addressing fields, and you just send it a message saying, hey, I want to read configuration or data or memory. And there's actually a lot of information out there on this because Intel, it seems like they just copy-pasted their internal specification into a patent. This is how you address it. This is all the devices on there, which is quite a lot. It's also what you, if any of you are kernel developers and you've had to deal with GPIOs on Intel SoCs, there's this P2SB device that you have to use. That's what the host uses to access this. Their documentation on it is really, really bad. Right, so this was all done using static analysis, but then I wanted to figure out how some of the logic actually worked, and it was really complicated, so I wanted to play around with VME. There was this nice talk by Ermolov and Goriachi, where they said, you know, you can now, we found an exploit that gives you code execution, and you can get JTAG access to it. Sounds really nice. It's actually not that easy. So arbitrary code in the execution in the BUT module, they actually describe their exploit and how you should use it. But they didn't describe anything that's needed to actually implement that. So if you want to do that, what you need to do, you need to figure out where the stack lives. You need to know, you need to write a payload that will actually get it from a buffer overflow on a stack that, by the way, uses stack cookies. So you can't just overwrite the return address to turn that into an arbitrary write. And you need to find out what the return pointer address is so you can overwrite it. And you need to find ROP gadgets because the stack is not executable. Right, so and then when you've done that, you can just turn on debug access or chain load a custom firmware or whatever. So what I did is I had a bit of trouble getting that running, and in order to test your payload, you have to flash it into the system, and it takes a while, and then the system just doesn't power on if the ME is not working, if you're crashing it instead of getting code execution. So it's not really viable to develop it that way, I think. Some people did. I respect that, because it's really, really hard. Then I wrote this. ME loader. It's called loader because at first I started out like writing it as sort of a wine thing where you would just map the right ranges at the right place and jump into it, execute it, patch some system calls. But because the ME is a microkernel system and almost every user space program accesses hardware directly, it ended up implementing like a good part of the chipset, at least as stubs or enough logic to get the code running. And I later on added some features that actually allow it to talk to hardware. I can use it as a debugger because it's actually running the ME firmware or parts of it inside a normal Linux process. I can just use GDB to debug it. Back in April last year, I got that working to the point where I could run the bootstrap process, which is where the vulnerability is. And then you just develop the exploit against it, which I did. And then I made a mistake cleaning up some old change root environments for closed source software, and I nuked my home dir. Yeah, I hadn't yet pushed everything to GitHub. So I stuck with an old version, and I decided, let's refactor this and turn it into something that might actually at some point be published, which, by the way, I did last summer. This is all public code, the ME loader thing. It's on GitHub. And someone else beat me to it and replicated that exploit by the Russian guys, which up to then they had produced a proof of concept thing for an Apollo chipset, Apollo Lake chipset, which worked completely different from what you had to do for normal ME. So that's actually, I was a bit disappointed by that, not being the first one to actually replicate this. But then I did about a week later. I got my loader back to the point where I could actually get to the vulnerable code and develop that exploit, and got it working not too long after. And here's the great thing. Then I went to the hackerspace. I flashed it into my laptop, the image that I had just been using on the emulator. I didn't change it. I flashed it. I was like, this is never going to work, and it worked. And I've still got that image on a flash chip with me because that's what I used to actually turn on the debugger. And then you need a debug probe because that USB-based debugging stuff that's mentioned here only works pretty late in boot, which is also why I only released the Apollo Lake stuff, because on those chipsets you can actually use this for the ME. And then you need this thing, because there's a second channel that it's using the USB plug, but it's a completely different physical layer, and you need an adapter for it, which I don't think was intended to be publicly available, because if you go to Intel's site and say, I want to buy this, they say, like, here's the CNDA, please sign it. But it appeared on Mouser. And luckily, I knew some people who had done some other stuff, got a nice bounty for it, and bought it and let me use it. Thanks to them. It's expensive, but you can buy it if it's still up there. Haven't checked. That's the link. So I'm a bit late, so I'm going to use the time for questions as well. So the main thing the ME does that you cannot replace is the boot process. It's not just breaking the system if you don't turn it on. It actually does stuff that has to be done. So you're going to have to use the ME anyway if you want to boot a computer. Don't necessarily have to use Intel's firmware, though. The ME itself boots like a microkernel system, so it has a process which implements a lot of the servers that will allow it to get to a point where it can start those servers. This process has very high privileges in older versions, which is what's being used on these chipsets. And if you exploit that, you're still ring 3, but you can turn on debugger, and you can use the debugger to become ring 0. So this is what the normal boot process for a computer looks like. And this is what happens when you use bootguard. There's a bit of code that runs even before the reset vector. And that's started by microcode initialization, of course. And this is what actually happens. The ME loads a new firmware into a power management controller. It then readies some stuff in the chipset, and it tells the power management controller, like, please stop pulling that CPU reset pin low, and the CPU will start. Power management controller is a completely independent thing. It's a 8051 derived microcontroller. Runs a real-time operating system from the 90s. This is the only string in the firmware, by the way. That's quoted there. Depending on the chipset you have, it's either loaded with a patch or with a complete binary from the ME. And it does a lot of important stuff. No documentation on it besides the ACPI interface, which is not really any useful. The ME has to do these things. It needs to load the keys for the bootguard process. It needs to set up clock controllers, and then tell the PMC to turn on the power to the CPU, needs to configure PCI Express fabric and reset, get the CPU to come out of reset. There's a lot of code involved in this, so I really didn't want to do this all statically. What I did is I added hardware support, hardware pass-through support to the emulator, and booted my laptop that way. I actually had a video of this, but I don't have the time to show it, which is a pity. But this is what I had going on. I had the bring-up process from the ME running in a Linux process, sending whatever hardware accesses it was trying to do that are important for boot to the debugger, and then that was using a ME in real hardware that was halted to actually do the register accesses, and it worked. So I was not going to show this. It actually booted the computer reliably. Then boot card configuration is fun because, you know, where they say they fuse in the keys. Well, yeah, but the ME loads them from fuses and then manually loads them into a register. So if you have code execution on the ME before it does this, you can just load your own values and you can run core boot even on a machine that has boot guard. Yeah, so I'm going to go through this really quickly. This is, by the way, these are the registers that configure what security model the CPU is going to enforce for the firmware. I'm going to release this code after my talk. It's part of a Python script that I wrote that uses the debugger to start the CPU without ME firmware. I traced all the accesses the ME firmware did, and I now have a Python script that can just start the computer without Intel's code. If you translate this into a ROP sequence or even into a binary for the ME, you can start a computer without the ME itself, or at least without it running the operating system. So yeah, future goals. I really do want to share this because if there's a way to escalate to ring 0 through the ROP chain, then you could just start your own kernel on the ME and have custom firmware at least from the vulnerability on. But you could also build a mod chip that uses the debugger interface to load a new firmware. There's a lot of stuff still needs to be discovered, but I'm going to hang out at the open source firmware village later, at least part of the week here. So, because I really want to get started on open source ME firmware using this. Right, and there's a lot of people that played a role in getting me to this point. Also would like to thank a guy from my hackerspace, Pino Affe, who basically allowed me to use his laptop to prepare the demo, which I ended up not being able to show. But right, I was going to ask whether there were any questions, but I don't think there's really any time for that anymore.
Peter, thank you so much. Unfortunately, we don't have any more time left.
I'll be around. I'll be around. So
I think it's very, very interesting because I hope that your talk will inspire many people to keep looking into how the management engine works and hopefully uncover even more stuff. I think we have time for just one single question. I don't know, do we have one from the internet? Thank you so much.
Okay, first off, I have to tell you, your shirt is nice. Chat wanted me to say this. And they asked how reliable this exploit is, and does it work on every boot?
Right, yeah, that's actually something really important that I forgot to mention. So they patched the vulnerability, but they didn't provide downgrade protection. If you can flash a vulnerable image with an exploit in it, it'll just boot every time on these chipsets. So 6th, 7th generation chipsets, put in that image, and it will reliably turn on the debugger every time you turn on the computer.
Thank you so much for the question. And Peter Boss, thank you so much. Please give him a great round of applause.